Okay, so we forgot to bring the camera to the back. So for those of you that are watching this, here's what we did. We had this solid disc, we had this ring, we let them roll down an inclined plane, and the short version is on the inclined plane, the solid disc rolled faster than the ring did because this ring, the mass is further towards the outside, it has a bigger moment of inertia, therefore it's tougher to get it to accelerate. Now, mathematically, and I don't write this down, I'm just going to show you how the math works. So mathematically, somewhere on here, there we go. And I would have to give you these formulas and I have to give you all these numbers. So if it's a solid disk, to calculate the moment of inertia of a solid disk or a solid cylinder, you use 1/2 mr squared. So the 1/2 comes from the idea that basically, on average, that mass is located halfway between the center and the outside. So that's where that 1/2 comes from. So if you plug in the numbers for these objects, you got a mass of 1/2 times 0.65 kilograms, and the outside radius is 0.075 meters, and you do all this math, and you get 1.8 times 10 to the negative third kilograms meters squared. Now, here's the problem with moment of inertia. A lot of times in physics, in case you haven't figured this out, you can get an answer and see if that seems reasonable, okay? Like, oh, how fast is the ball going when it hits the ground? Okay, I didn't drop it really far, it's not going really fast, okay? What's the velocity of a bicycle? 10 meters per second seems reasonable. Moment of inertias are tough, mainly because of the fact that you don't have an intuitive sense and go, oh, that seems like a reasonable number because it's mass and radius squared and all this. So, but you can at least have an idea. The Earth, as it spins, has a moment of inertia. And it's a really, really big number because we have a lot of mass. And once that mass is spinning, then it tends not to want to slow down, which is a good thing. We don't want the Earth to start rapidly slowing down, which would be bad. Because, well, how long are our days? Well, 24 hours, all right? Even in the 58 years I've been on this Earth, that really hasn't changed much. So if all of a sudden CNN comes in and says, oh, hey, Earth is really going to start slowing down. Oh, bummer. Because the bad thing about that is the nights are going to be longer, so the temperature is going to drop more. Days are going to be longer, so the temperature is going to go up more. So you're going to have a much more magnified change in temperatures between daylight and sunlight. That and the fact the water in the oceans would tend to keep moving and bad things would happen. Okay, now, if you have the Lord of the Rings, well, again, I would have to give you these dimensions. But for a ring like this, you have an inside radius, what you're going to call R1, which is 0.070 meters. You have an outside radius, R2, which is 0.075 meters, which is why these are the exact same, because they both have the exact same outside radius. They have the same mass. Now, this is where this gets a little bit more complicated. So this moment of inertia is 1/2 m R1 squared plus R2 squared. If generally you do this in Calc 3, if not differential equations, but one of the things you do is that you figure out where these formulas come from, because it has to do with the distribution of mass and taking integrals and all this other stuff. So here's the point. If you plug in the numbers, the mass of the ring, inside radius, outside radius, and all that, you're going to get, out of this calculation, 3.4 times 10 to the negative third kilograms meters squared. So mathematically, when you look at these numbers, that solid disk has a moment of inertia of 1.8 times 10 to the minus third. Lord of the Rings has a moment of inertia of 3.4 times 10 to the minus third. This has a bigger moment of inertia. That's why when I let them go and they roll down the ramp, that's why the solid disk won. Because it had a smaller moment of inertia, therefore it was easier to speed up. Now, here's what I want you to see at this point, is that there's an inverse relationship between moment of inertia and angular acceleration. So, if the moment of inertia gets bigger, your angular acceleration becomes smaller. Okay? Now, there's a key assumption that's made. The key assumption is that you are applying the same torque to the object. Okay? That's a huge caveat, and mathematically you'll see why that's important later on. If you're applying the same torque, which is what we did when we let them roll down the inclined plane, same thing, everything was the same. That's why this happened. Now, here's how some people like to remember this, is that big fish have small eyes. Oh, come on. Erase. So what that means, and if you want a visual on this, here's a big fish, and it's going to have a tiny little eye. So it's an inverse relationship. Again, if it's the same torque, and this is going to be a huge caveat, if it's the same torque, then there's an inverse relationship, because the bigger that moment of inertia is, the harder it is to get it to accelerate. Now, if you like, well, I like small fish, I'm into guppies, you can reverse it. You can say small fish have large eyes, okay? If you're into guppies, hey, reverse it, all right? Doesn't make any difference. Just understand that there's an inverse relationship between the two. Okay, now, next step. So here I've got this bicycle wheel, right? Is this thing going to have a moment of inertia? Andrew?
Yes.
Why?
Because it has mass.
And? It has a?
Radius.
Radius. Oh, it has a moment of inertia. It has mass and radius, okay? Electrons have moments of inertia. They're really, really small. But anything that has mass and has the capacity to spin is going to have a moment of inertia. Okay. So here's the question. It's at rest, and then I make it spin. Sydney, in which situation does it have a larger moment of inertia? When it's at rest, or when it's spinning?
They're the same,
Or it's the same. Why is it the same?
because the mass and the radius haven't changed.
Mass and radius haven't changed. Okay? So whether an object is spinning or not doesn't impact the moment of inertia. Okay? Because it's only dependent upon mass and radius. And as long as those two values are the same, it doesn't matter. It's the same thing with inertia. Whether this 1 kilogram mass is moving, or if it's at rest, it's still going to have the same inertia. So whether an object is spinning or not does not impact the moment of inertia. Cool with that. Okay. Now, I'm going to say something very, very important, and you take heed of this. When you're talking about making an object spin and accelerate, the equation that you are forbidden from using when you're talking about a wheel accelerating, and I know this flies in the face of everything that I've taught you up to this point in time, you are forbidden from using F equals ma. Okay, you are forbidden from using it. You cannot use it. And here's the reason why. If I apply a force very, very close to the center of this, I get a certain acceleration of the wheel. But if I apply that same force out here on the edge, I get a completely different acceleration. So, because of the fact that torque impacts your acceleration, and torque has two variables, it has force and where that is applied, This is why you cannot use F equals ma on spinning objects. The only time I could use F equals ma is if I was just going to throw this thing at Chloe. It's like, Chloe, catch, okay? And I just throw it, okay?
Charles. Throw to Charles.
No, I'm not going to throw Charles, okay? Well, I might. Anyway, so throwing the wheel, hey, F equals ma, makes sense, perfect. Making it spin, you can't do that. Now, as I say that, even though I just told you not to use F equals ma, I'm going to use F equals ma. It's like, you just told us not to. There's the method of my madness. So, we just said that F equals ma, and torque equals force times radius, right? True?
Yes.
Good. Now, here's the story. If I solve this for force, I get torque over radius equals force, right?
Yes.
Cool with this. No, nothing magic, right? So I'm going to take torque over radius and substitute that in here. So I'm going to have torque over radius equals mass times acceleration. But we're not talking about linear acceleration, we're talking about angular acceleration. So what's the equation that we talked about yesterday that crosses the bridge between linear acceleration and angular acceleration? A equals what?
Radius alpha.
R alpha. So could I take R alpha, or R fish, and put that into here?
Yes.
Legal? Absolutely. So I've got torque over radius equals mass times R fish. Now, I want to multiply this R over here, and then I get the pirate's favorite equation, because then I get torque equals mr squared times alpha. Okay, nothing fancy. All I did was some substitutions. But what does mr squared equal?
Oh, like inertia.
Moment of inertia, right? General form, moment of inertia. So I can write this as torque equals I fish, which also equals force times radius. So torque now equals two things. It equals I alpha, and it equals force times radius. Now, if this is going to be valid, Chloe, what has to happen to the units on both sides? They have to be the same. If I don't get the same units on both sides, no matter how cool that voodoo was that I just did, if I don't get the same units, it's dead in the water. So force is Newton meters, which is kilograms meters per second squared times meters, which gives me kilograms meters squared over second squared. Cool? So another way to write this. It's much more complicated, but it works. Now, over here, moment of inertia is measured in what units?
Kilogram meter.
Kilograms meters squared, right? Any I is in kilograms meters squared. Alpha is in what? Sydney?
Meters per second.
No.
No.
Radians per second squared.
Radians per second squared. But radians are a dimensionless number,
The only dependent on
so we don't worry about that.
Yes.
So basically we get the exact same thing. Kilograms meters squared per second squared on both sides. And if we didn't, the equations aren't going to work. Okay, now let's talk about the spinning wheel. So this is why you can't use F equals ma. So if I apply a force with a small radius, then if you look at torque, I've got a force multiplied by a small radius. And that's going to equal I alpha. So this side doesn't impact that side. Moment of inertia is a fixed value. So if I don't generate very much torque on the force radius side, I don't get a very big acceleration on the other side. Because it's not, it's just a small number, right? But if I apply that same force way out here on the edge, then I've created a lot more torque. And now if I create a lot more torque, I'm going to generate a bigger acceleration. So that's why I said don't use F equals ma. Because where you apply that force greatly alters your angular acceleration. So if you wanted to, if you could look at a graph of force and radius. Okay? So in that first situation, I applied a force with a really small radius. So that was a certain amount of force with a small radius. Now, Deacon, what does the area underneath that force radius graph represent? Do not make this difficult.
8 meters.
Otherwise known as, it rhymes with orc. Torque, because it's force times radius. So this area represents the torque. Now, if I apply that same force, but there's a much bigger radius, Deacon, what's going to happen to the amount of torque that's generated? It's going to increase. What's going to happen to the angular acceleration?
It's also going to increase.
It's also going to increase. Okay? Cool with that. All right. Last equation. Oh, shit. And that's L equals I button.
I wonder what this is.
Oh. There's your moment of inertia. And that's angular. Why are you being stupid? Velocity. Okay. So let's compare this to linear momentum, which is equal to mass times velocity. Okay? So what they have in common is that the letters that represent momentum and angular momentum, they have nothing to do with, like, you have L and you have P. Okay? So they both got screwed in terms of, hey, what are we going to use to represent it? So if you think about this, even though they look completely different, what they represent is the same. So this is mass, which is a measure of inertia, how hard it is to get something to speed up or slow down. That's I, moment of inertia, which is how difficult it is to get something to rotate. Okay? So they're both, the first variable is both measuring a resistance to a change in velocity. V, well, that's how fast you're going. Omega, that's how fast you're spinning. So even though they look completely different, fundamentally, you're multiplying together the same two physical quantities. A resistance to a change multiplied by how fast it's spinning. Now, the units get a little bit jacked up with L. They're not near as cool as the momentum. So you have L equals I omega. So you have I, which is kilograms meters squared, and then you have omega, which is radians per second. Okay? Radians are there, but we don't talk about it because it's a dimensionless number, so it's kilograms meters squared per second. Kind of a jacked up deal, but that's just the hand that we're dealt. Now, angular momentum is a vector quantity, just like linear momentum is. Now, to determine the direction of linear momentum, that's simple. Is it moving in a positive value or is it moving in a negative value? Velocity can be positive or negative. Hey, which direction is it moving? So, angular momentum, to determine the direction of that vector, you have to use what's known as the right-hand rule. Okay? We're going to use the right-hand rule with angular momentum, we're gonna use it with electric fields, eventually we're gonna use it with magnetic fields as well. It's always the right hand. So this is how this plays out. So I'm gonna take this and I'm gonna rotate the wheel in this direction. So what you do is, you take your right hand, hence the term right hand rule, and you take these 4 fingers and you curl your fingers in the direction that the wheel is spinning, okay? So I'm gonna spin it like this. So what that means is that I'm just gonna go out like this. This is the direction I'm gonna curl it. So then my thumb is pointing out this way. So the direction of the angular momentum vector, imagine it's like a lightsaber, and so that's pointing out in this direction. The faster I spin it, it's still going to be going in that same direction, but the faster it goes, the bigger that angular momentum vector is going to be pointing out this way. Now, if I spin it like this, then you take your right hand and you curl it in that direction, because that's the wheel that was rotating in that direction. Then the momentum vector points out this side, okay? Now, this is how this applies to bicycles. If this isn't spinning, and I let go of it, it falls over. Right now, does this thing have a moment of inertia? Sydney?
Yes.
It does, mass and radius. But does it have angular momentum?
No,
Why?
it doesn't have a velocity.
Yeah, it's not spinning, okay? But if I take this thing and I spin it, okay, and then set it down, then it stays upright. So in this situation, the wheel is spinning around like this. So if you do the right hand rule, you take your right hand and you spin it in this direction. My thumb is pointing down. So I would say the momentum vector is pointing into the table. It's pointing down. Now, if I reverse this thing and I spin it in the opposite direction like that, then I take my right hand and curl it this way, then the momentum vector is pointing up. Okay? So to determine the direction of the momentum vector, you wrap it in the direction that it's moving. Whichever direction your thumb is pointing, that's the direction of your momentum vector. Cool with that. Okay, Dylan, I need your help. So you might give that a little bit of a spin.
What?
The camera.
Oh.
So I need you to stand on the green spinny thing. Okay? Hold this. Okay, now, here's what I'm going to do. Is it possible for Dylan to change his moment of inertia?
Yes.
By doing what?
Changing the distribution of mass.
Yeah. So if you put your arms out, what's happened to his moment of inertia?
It's increased.
It's increased. Brings it in, it's gotten smaller, right? So he can change his moment of inertia. Now, right now, Dylan, how much angular momentum do you have?
0.
Why?
It's not moving.
You're not moving. So here's what I want you to do. Do you think angular momentum has to be conserved?
Yes.
Yes, one of the great conservation laws. Linear momentum has to be conserved, angular momentum has to be conserved. So here's what I want you to do. I want you to take this, okay, and I want you to take the top half of your body and move it to the left. Okay? Now, when he does that, now go back the other way. When he does that, when he takes the top half of his body and moves it in one direction, what happens to the bottom half of his body? It goes in the opposite direction. Why?
Because the momentum at the end has to equal the momentum at the beginning.
Beautiful. The momentum still have to add up to equal to 0. So this is why he can't do this and have his legs go in the same direction. Because then you would be creating angular momentum. Okay, now this is going to require a little bit of balance. Okay? Not much. So, put your arms out.
All right.
And I'm going to apply a torque to you, and I'm going to give you some angular momentum. Okay? Then, and stay centered on the green spinny thing.
All right.
Then, once I get you spinning, then I want you to bring your arms in like this.
All right.
Okay, so you're going to be out like this.
I'm gonna be spinning
and then then you're gonna bring the arms in
while I'm spinning.
while you're spinning.
Alright.
Okay? All right, you ready? Oh, no. Wait until I'll tell you when to bring him in.
Alright.
Okay, you ready? Now, bring him in. Now, when he brought those arms in, what happened? What did you do?
I sped up
You sped up. Why?
because my inertia went down.
Did you have the same angular momentum?
Yeah.
Okay, so L equals I omega, right? So when he brought his arms in, his moment of inertia became smaller. So to compensate that, the omega had to get
Bigger.
bigger. Okay, we're done. So here's Dylan. So L has to be conserved. So situation number one, here's Dylan, and he's got his arms out. Okay? So with his arms out, what do you know about his moment of inertia? Big or small?
Big.
Big. So in this situation, he has a big I. I applied a torque to him, and I gave him a certain rate of spin that he was spinning at, right? Okay? So therefore, he had a certain amount of angular momentum. Okay? Big radius, big I, there you go. Now, when he brought those in like this, okay? When he brought those weights in, Dylan, what happened to your moment of inertia?
It decreased.
So now he had a smaller moment of inertia because it brought the radius in. So to compensate, to produce the same angular momentum, what did you have to do?
My angular velocity increased.
Yeah. So he had to spin faster to produce the same angular momentum. So if you've ever seen ice skaters, okay, when they put their hands over their head, right, they spin really, really, really fast, and when they slow down, they put their arms out, it's just angular momentum. If you see someone diving off of a high dive, if they want to spin really fast, they're going to be in like a tuck position. They're going to decrease the radius. If they want to slow down, they're going to extend their bodies, increase the radius, and they're going to go slower. So you can also show it, so give this a spin, over the camera. So this is what's known as a Hoberman sphere. And you can change the radius of this thing by pulling on this. So I'm going to give this a spin. Now I've given it an angular momentum, spinning at a certain rate. So if I collapse it, what does it do?
Speeds up.
Speeds up. If I lower it back down, then, well, that is just getting twisted up there. Hold on. Let me untwist it. So if I start with it small and spinning, as soon as I drop it, it slows down. So if you ever study like hurricanes are the classic example of this. So hurricanes have a tremendous amount of angular momentum. They're spinning. So this is why the winds closer to the eye of the hurricane are much stronger, because of the fact they're closer to the center. And they have to have the same angular momentum as the points further on the outside. Okay, now, Dylan, when I made you spin, did I apply a torque to you?
Yes.
Did I change your angular momentum?
No.
Yes, I did.
Oh, okay.
Because how much angular momentum did you have at the beginning?
I had, zeros.
You had 0, okay? So, hopefully this makes sense. That the change in angular momentum equals torque multiplied by time. So hopefully this makes sense. So if I apply a certain torque to Dylan, and if I apply it over a very short amount of time, so imagine this is Dylan. So if I apply a torque over a short amount of time, I don't change this angular momentum very much. But if I apply that same torque over a longer period of time, that's going to create a greater change in angular momentum. Now, again, the units have to work out. If they don't, then it doesn't make any sense. So angular momentum, we said, was kilograms meters squared per second. True? Good with that. So torque is going to be in Newton seconds, or Newton meters, which are kilograms meters squared over second squared. And then we've got time, which is going to be in seconds. So that's going to cancel out. I get the same units of kilogram meters squared per second. Miracle of miracles. Life is good. Okay, so stop, you on the camera.